The views in this episode represent those of my guests and not of anyone in any of the government departments. And the episode was recorded back in March 2025. Welcome to an episode of Beta Talk. This is one of our Heat Pump Ready episodes where I speak to people who have been involved in the Heat Pump Ready project. And today I'm joined by Andreas Fechs from Kensa Engineering, Jonathan Siviter from a company called, and he'll correct me if I'm wrong, T Conversion or Tech Conversion. And we've also got Ren Kang from Mixergy. So, Jonathan, I suppose I'll come to you first. Did I get that right?
It's Thermoelectric Conversion Systems.
Right.
We usually shorten it to either TCS or TE conversion.
Fantastic. And that's something that uses the Peltier effect. So that's what I would call sort of solid state stuff. Have I got that right?
Yeah, that's right. There's no moving parts in it. It's entirely solid state based. So it's a semiconductor material that sits in between two ceramic plates. And you put a DC current through that semiconductor, and that essentially causes what you could call a phonon transfer. So it's a heat particle or wave moving from one side of the device to the other. So on one side it gets colder, and on the opposite side it gets hotter, without going into all the semiconductor physics that implies.
And
it essentially acts like a heat pump.
Yeah, and I mean the advantage of these is you can sort of change polarity and sort of change where you move heat, so you can have it as a cooling device and
yeah. So you can also change the magnitude as well. So how much heat or how much cooling you're doing by changing the voltage and current that's applied to it. So you can switch the polarity. So you can change it from heating on one side to cooling on the opposite side. And then you can change how much heat you're passing or what the temperature difference is by changing the voltage and current across it. So that's essentially what we've packaged and been developing as part of our project.
So it's very interesting stuff, this. So when people talk about heat pumps, obviously they're aware of vapor compression systems, where we're moving energy from an evaporator to a condenser via vapor compression. But people probably aren't aware of this Peltier effect and solid state. And so, I mean, there's another company I know of that does it. I mean, I'm not too sure how many companies are doing it at the moment, but funny enough, I've got a meeting with some MBA students who are doing some market research into this type of technology. I've got that coming up soon. So I find it very, very interesting because it's obviously got some advantages. It hasn't got a refrigerant, hasn't got, like you say, moving parts. So there's all sorts. So we're going to come back to you and discuss sort of what you've actually been doing on the Heat Pump Ready project. I'm just going to introduce Ren. Ren, you're from a company I know well, Mixergy.
Yes, thank you. Yes.
How long have you been with them? Have you been with them for quite a while?
Yeah, I was one of the co-founders, so with Pete Armstrong, my friend and my colleague back in time when we were both DPhil students at the university. We're working towards using a smart hot water tank to provide great flexibility. That was exactly 10, 11 years ago. So that's how the project or company has been originated.
Wow, is it that long? Crikey.
Yeah.
Time goes so quick, does it? So I think one of my engineering friends, and I'm recording him tonight actually, Damon Blankmore. I think he came put the Mixergy in at your headquarters.
Yeah, we've known each other for a long time.
He's a great engineer. So how have you been involved in the project? Tell us a bit more about how Mixergy got involved in this program.
Yeah, so basically we recognize the lots of challenges around the heat pump installation and heat pump deployment. One of the problems is that the complexity of the installation and how efficient they can be operated, and how you operate it could be impact its efficiency. So essentially, we are integrating. So every heat pump needs to have a hot water tank to provide hot water storage, and it needs a separate buffer vessel for the heating system. And effectively, your hot water tank is a thermal storage, because Mixergy has been long developing the intelligence around the hot water systems, and we know how much hot water you use, and we know the thermal content, and we kind of extrapolate the thermal content in a way that we can effectively integrate the space heating buffer vessel into the hot water system. So we're kind of simplify the installation, reduce the installation cost, and in the same time, we are having a more comprehensive control over with a heat pump, so that we can impact its operations, such as controlling the operating temperature and then controlling when to turn on and turn off based on the tariff information and usage condition. So that's a technology we're developing through this project.
Did you have any of these your Mixergy cylinders installed anywhere for this to be
Yes,
studied?
so we carry out a trial where we install 10 Mixergy we call ATI system, which is called aggregate thermal inertia system, and 10 conventional system where you have the hot water tank and separate buffer vessel and with a standard control over heat pump in a trial. It's still a bit of commercial sensitive because it was carried out with a commercial partner, which is not, we won't be able to release their names at this stage.
Okay,
But initial trial has shown some promising outcomes, and which goes beyond, which actually achieve our initial target of energy saving.
Did you have any other? You mentioned you can't name one specific, but did you have any consortium partners within your?
Yes, we've been working with Valent and Centrica in this project. Valent being mainly working on the commercial exploitation of the project, and we'll be conducting separate trials with Salford Energy Homes, and Centrica is mainly around the heat pump testing and heat pump trials.
Fantastic.
Yeah.
Andreas, so you're Kensa Engineering. What have you been doing as part of the Heat Pump Ready project?
Well, I've been project managing it. That was basically, in fact, I was actually hired by Kensa specifically for this project. So I've accompanied it not right from the start because the project originated before I joined, but I've basically accompanied the entire development as the project manager.
And as some of my listeners will know, we had there was a Heat Pump Ready project, Stream 1, and then there was Stream 2 projects. Now this is a Stream 2 project, isn't it? That you're involved
Yes,
in?
that it is Stream 2.
Yeah.
I guess we were also involved in Stream 1 because we were developing the concept of superheat recovery for a while, and had to make our bitter learnings on the way, and to the point where we have now mastered it. So basically, in Stream 2 we could complete what we started in Stream 1.
So just dive into sort of the weeds, as they say, and sort of tell us a little bit more about what you've been actually doing in Stream 2 for the project. Did you have stuff did you have any of the shoeboxes installed anywhere, and were monitoring them?
No, that was part of Stream 1.
Yeah.
We had not shoeboxes, sorry, storage heat pumps in the field. For Stream 2, it was all in-house testing and in-house development work to get the technology to a state where where it's actually as good as ready to be commercialized. That was the scope.
And is that technical? Is it different to the shoebox then, or are you just trying to develop the shoebox further?
No, it is different insofar as it is a storage heat pump. I mean, the shoebox is a heat pump, and that's the end of it. The storage heat pump has PCMs, which are phase change material heat storage included in the unit, so it is capable of charging those and obviously then discharging them when the heat is needed. That was the scope of this project, to be able to utilize night tariffs and to be able to ease the load on the grid. These were basically the two. Well, and the night tariffs make it also cheaper for the consumer, obviously, because you're using a better tariff than your peak tariffs. That was the scope of this project.
Got you. Did you develop or did you design and develop your own PCM, or did you use some of the PCMs that others use?
No, we used off-the-shelf PCMs, actually quite deliberately. We didn't want to make a PCM and heat exchanger development part of the project as well as everything else, and so we are using existing PCMs, and yeah, they work. We had to change the scope slightly because we have now a heat pump that is a flexible storage heat pump, but without superheat recovery. I'll get onto this in more detail later on. And we have developed the technology to control successfully superheat recovery. We do need a suitable PCM for it, which has been withdrawn from the market. So we have a solution for now. We have a solution for the future as soon as this gets available again, becomes available again.
I mean, I suppose for some of my listeners who are probably not familiar with phase change materials, I mean, there are different types, and I suppose are there concerns with different types over safety or what they're made from? Because that's something they might want to know.
Yeah, the good news here is it's actually a fantastically safe material. In fact, it's almost edible. So, that's actually one of the bonuses, that there is no negative environmental impact using phase change material. It's a kind of wax. So, and the advantage of the material is that when it gives off its heats, while it goes through the phase change, which is in this case from liquid to waxy substance, it gives its heat off at a constant temperature. That's what makes it a very attractive medium for heat storage. And there's absolutely no safety concern. It's perfectly safe, and actually its environmental credentials are superb, because obviously you could, for instance, use a battery for energy storage and just run a heat pump with it. That's one way of doing that. But batteries have their own environmental problems.
So it all sounds like everyone's doing some really, really exciting stuff. So coming back to you, Jonathan, you're using what we call solid state or thermoelectric systems. Did you have anything out there in the field, or was this sort of because you're in stream 2 as well? Was it this more about sort of developing the technology for further, when we can get to the point of putting it out in the field, or did you have stuff out in the field?
Yeah, we didn't have stuff out in the field for this. We spent most of our time developing the sort of core technology. Most of our sort of work prior to this call was mainly in cooling systems, actually. So actually providing, several hundred watts of cooling capacity at a delta T. And what we were finding is that we had a challenge in kind of getting rid of the heat. And this sort of heat pump ready competition came along at the point where we were thinking of, okay, we can do something useful with this heat. We've been mainly using it to cool cabinets, to cool systems, to cool, something that's environmentally maybe sort of protected, an IP rated cabinet. But this was an opportunity to really explore what you can do when you flip it into doing something useful with the heat. So we sort of started with the concept of a flexible heat pump using our tech, and that developed into essentially coming up with a standard, our standard Hummingbird heat pump, which is essentially a 4 or 5 kilowatt rated thermal output heat pump, all in the size of about a desktop PC. So it's about this, and it weighs about 25 kilos in total. And you can couple either with a water source or an air source. I call it water source or air source. I don't mean it's actually using a refrigerant. I mean, it's either a fan coil unit for your air source or a water loop for your water source. So it's trying to be as flexible as possible. And that kind of fitted in with what the project set out to achieve. And I think it's been incredibly successful, because we've now come to a point where we've almost got a product that we can put through the sort of accreditation you need to do with the MCS, get ISO 9001, all the bits and pieces that enable people to access the various grants that are available, not just down south in England, but also up in Scotland and further afield to exploit the tech and get it into homes. Because our sort of focus point for this was trying to make it a system that can be retrofitted into a house, or it can be put into somewhere that's hard to decarbonize. So our sort of focus was looking at flats and apartments and other areas that you really were struggling to fit traditional air source units. And so we sort of started from the point of, okay, well, what size of unit could we build up, still get a reasonable heat output and a good COP from it, and then be able to let people install that and keep it quite kind of simple. It runs off a 13 amp plug, all the sort of stuff that when you get into installing a heat pump, you need to consider. We've tried to sort of not because of how the tech works. Some of the things you don't need to worry about. System volume is another one. We've essentially got a 0 to 100% control over the heat output, and because of that, there's no minimum. So there's no minimum turn on frequency, if you like, for a compressor, because it's all in DC. You can turn it on to whatever rate you need at whatever temperature you need, and it'll provide it. And the output control is as good as really you want. Less than 1% control is easy.
Yeah, it's incredibly variable, isn't it?
Incredibly variable. Yeah.
So you've got, I suppose, the advantage you don't have to have an outside unit. So you've mentioned space, and some housing archetypes are going to maybe struggle with finding space to put an outside unit. Crikey, very light. We're talking 25 kilograms, aren't we?
It's super light. There's
Yeah.
really not much in it.
And
a lot in it.
and like you said, these can kind of then be kind of attached to a wet sink system. So like obviously someone that's using radiators or underfloor, you know, that's the sink system is wet, getting rid of the heat, and or it can be to air sink systems like what we've everywhere in this country. We've got air to air.
Yep.
Air to air is heating all sorts of commercial build. I mean, people often think heat pumps are new, but they're literally everywhere in this country, everywhere. And you mentioned things like, I mean, there's millions and millions of cooling cabinets on this planet, and vending machines. You know, they all use vapor compression heat pump systems. That Costa coffee machine in a petrol station is using a vapor compression heat pump system to keep that milk at a legal temperature. But your technology is good for that type of stuff as well, isn't it? And is that where it got born from? You mentioned things like cooling cabinets, and then you think, oh, we can actually use it for sort of heat pump heating systems.
Exactly. That's kind of where we started our journey. We'd had some funding to develop the sort of the cooling capacity and sort of the various ways to cool. So yeah, it was air to air or air to water or water to air, water to water, those sorts of various combinations you get for moving energy. And I think where that's the project sort of was born out of is the ability to take what we had in cooling, but adapt it and make it more sort of suitable for fitting into wet heating systems, which we're pretty familiar with in the UK. But that also extends further afield because it's far more prevalent in almost every other part of the world to have, and including the UK, to have air-to-air vapor compression systems. And so the sort of system we've been able to come up with can kind of exploit both parts of it. You can use it in an air-to-air sort of setup. You can use it in an air-to-water, water-to-air. All these combinations are possible. So it's incredibly flexible. But of course, being jack of all trades is usually master of none. So we've got a chance to focus a little bit in this system, in this application, this heat pump ready scheme, to focus on the domestic heating market at a particular sort of capacity and performance, and then sort of focus on deploying that. And that's really what's next.
Did you have any consortium partners?
No, it was just us.
And obviously, as you'll know, theoretically, this kind of stuff has very high coefficients of performance. Have you managed to test your COPs at all on any?
Yeah, so we're going through the 14511 testing at the moment, 14825, the EN standards that sort of govern SCOP and COP performance at various different temperature differences. And I think that's where sort of some of the stuff that obviously suits vapor compression, because it's very good at producing a constant, say, flow and return temperature. Ours is far more flexible, which I guess our average COP is probably about 5, which is pretty good for compared to vapor compression. But as you start at low delta T's, so between your ambient and your sink, let's say you've got a few degrees delta T, our COPs are enormously high. They're well over 10, well over 15. But as your temperature difference increases, so you get to sort of our maximum delta T we can go to is probably about 70 degrees C between the ambient and source. Our COPs at that point is probably about 1.5 to 2. So it's about managing that curve as you go from big delta T's to wee delta T's to get the most out of the system.
Sounds super interesting. Ren, coming back to you. So obviously, I think most of my listeners, like I've alluded to, are going to be very familiar with Mixergy because, like you say, you've been going around about 11 years now, and that time seems to have flown for me because I remember when you came out. So tell us a little bit about your journey from and what you've learned in that decade, and specifically tie it up with what you've learned from this project that's helped you because when you came out, obviously some of us engineers thought, well, it's just another cylinder that's got some clever things that can heat up. For instance, it can kind of control sort of the thermocline, the stratification going on in the cylinder. But as a lot of us engineers sort of got to know the technology, we started to like it lots. I've just mentioned Damien Blackwell, one of my favourite engineers in the UK. He likes it. Tell us what you've learned over the period of time, and then more specifically what you've learned with the program.
Yeah, sure. Well, the first thing we know about this hot water cylinder, hot water industry is quite an overlooked industry, especially for the energy it uses domestically. If you think about the hot water storage systems, more than 50% of the UK household has a existing hot water system in situ, and especially with the future electrification of heating industry, every heat pump will need to have a hot water tank and have form of thermal storage system. Hence why this will be a quite crucial or important path to our net zero. So we need to put in a lot of innovation to make sure that we make best use of the hot water system. And the second thing is that people don't look at it, their hot water tanks very much. They might get a bit of exciting the first time they got a new tank, but so the key thing that Mixergy does is that we put it in, and then we're trying to use the machine learning or a smart control algorithm to optimize it in the background. Try to not let users to worry too much about it, because because the way we design the system, we have the sensor attachment which measures the hot water tank across different level of points with a single strip of sensor. So the exact energy content, just like your battery. It gives you percentage like state of charge. And then the way we charge it is also because we stratify the system, so we heat the system from the top down. So effectively, we can heat a certain amount of energy if we need it to. So we are making best use of of the hot water, the volume of the hot water. Make sure they don't heat the amount of water that they don't need. So hence why saving the energy. And from the learning that most of the user, because when they first specify the hot water tank, they usually specify based on the property size. In fact, they don't have that many people needing such a big hot water tank for the demand. They might need to if they have a guest over for Christmas or for guest night, but most of the time they only use less than half of the tank. So we could save quite a lot of energy just by not heating what we don't need. And then that's our journey around the hot water systems. Now we're coming to the heat pump era, where we're trying to electrifying the heating industry and electrifying the transportation industry. Now it's the heat pump just doesn't work alone by itself. So we are more like or called home energy management system. It should be considered as a part of the home energy management system, not the heat pump alone, not hot water alone, not space heating alone, and not the EV charging alone. Because how people heating their system, when do they heat it, and based on what tariff they have, and based on what outdoor condition is, what significantly impact the heat pump's efficiency. So throughout this project, we're not just develop the hardware innovation around aggregating the thermal inertia into the hot water system. We're also developing the control system and the whole ecosystem around the heat pumps, like for space heating control, hot water control. And along with the trial, we'll also have the EV chargers, so we can actually altogether, we can determine what's a great interaction we do, how we make sure you don't turn on the heat pump at the same time you turn on your EV, for example, to increase the network stress for the whole grid. Hope that makes sense.
Yeah, the home energy management systems is as you know, is a big piece, isn't it? That lots of people become interested in.
Yeah.
And we can stay on that point of home energy management systems. Is that something you've been looking into as well, Andreas, or has Kensa been looking into? When you're charging your PCMs, when you're letting it go, and whether you're hooking up to batteries and stuff like that, as well as your heat pumps? Is that something of a wider thing?
Yeah, I mean, it was definitely part of the project. We were also developing a new controller for the heat pump, which was required for a storage heat pump, and that is, of course, smart thermostat compatible. So that was a cooperation. We didn't develop that ourselves, and it will also be, once it is in place, DSR compatible, because it is actually exactly managing, as Ren just said, managing the entire system is actually the key to making this work 100%. We actually had PNDC, the Power Network Distribution Center of the University in Strathclyde. They investigated the impact storage heat pumps can have, and if you don't control the system and everyone works of one tariff, you would go up to 16%. That would be the sweet spot. You can actually achieve much more, but then you have to be able to manage which heat pump in which area, or pumps plural, are turning on at the same time to charge, because otherwise you end up with the exactly same problem as you have today, that when it gets cold outside, all heat pumps turn on. And yes, that was part of it, and we obviously made sure that it is future proof to co-op with a DSR and use a smart thermostat.
The actual, so your this particular type of unit, is it using the same technology as, let's say, your shoebox does? Because obviously people who know your shoebox knows it uses sort of different components of what other manufacturers you use, like you've got fixed speed compressor and stuff like that. Have you used the same sort of components from your shoebox within this particular unit with your phase change?
Similar. The one major difference is that we were using a variable speed compressor, which the shoebox doesn't have. Shoebox is single speed, which does enable you to either run the compressor really efficient, or to blast as much energy into your heat storage in a shortest possible time, if that's what's required. So the component, and otherwise it is still, of course, a refrigeration circuit, so that is the same, but the components are slightly different. And a large part of the project was the superheat recovery, which that this is where Ren's and our project have one similarity here, because superheat recovery is all about producing hot water more efficiently. So just to explain that briefly, when the refrigerant comes out really hot, it has the ideal temperature to heat up water. But if you all put that into one storage element, you lose the ability to siphon up that high heat. It just goes in your general storage. The superheat recovery works with two different temperature storage units, a higher one that basically takes the refrigerant in as it comes from the compressor, stores the heat at a higher temperature, and then it goes into the next storage unit, which stores it at a lower temperature, suitable for space heating. And the trickery came in because we obviously tried that before, and the effect was that we would overheat the first storage element, because we couldn't control the heat coming out, and we couldn't control the charge level between the two storage mediums. We have mastered that now, and it basically boils down to having to be able to control both the charge level of the PCMs by through another heat exchanger, and also the draw level. And with that, we actually achieved the direct hot water efficiency with storage by 20% COP increase by doing that. So all that has been considered, and will in the future also be working with smart thermostat and DSR systems. And as I said, I think this is a major requirement actually, if we want to get the maximum benefit out of all these systems.
And just for my listeners, just because obviously a lot of my listeners will be familiar with Kensa and ambient loop systems, and where you'll get this little shoebox going into individual homes, flats, for instance. So what you're describing here how big is this thing? Is this going to be sort of something that's in a central plant station, or is this for people's individual spaces?
Um, that is, of course, I mean, one reason why we use PCMs, because it can be achieved not as efficiently, but it can be achieved with water storage as well, what we're doing. One reason we chose PCMs is because they take about half the space to store the same energy as a water cylinder, roundabout. And of course, still, the unit turns out to be big. That was actually the one major challenge we had. It is about the size of a fridge freezer unit, and we actually had that was one of the challenges we had to sort out to be able to install it, because it's also heavy, of course. We actually designed it in two parts that are then put on top of each other at the point of installation, but only need water connection. So there's no refrigerant circuit that needs to be manipulated at the point of installation.
Mm. I'm assuming it's going to be quite heavy as well with PCM. Is it?
Yes, it's obviously the weight is probably the same today, but you put in the water cylinder empty and then you fill it. That is the big difference. Whereas the unit we developed weighs about 450 kilos in total, and consists of two elements, round about half the weight each, which are then installed.
Yeah, so that's kind of equivalent then to a 450 litre cylinder, isn't it? Because obviously, as water at 4 degrees will have a mass of 1 kilo per litre.
Pretty much, yeah.
I mean, that's the interesting thing about PCMs, because yes, they are space saving, but they can end up being quite heavy units, can't they?
Well, they're not heavier than water, just that you can't fill them at the point of installation. That is actually the key difference.
I suppose it's the gubbins all around them, isn't it? And that's involved with them. Because obviously a cylinder is just a cylinder until you fill it with water. And it's not really much else. Well, you've got your element and maybe a core. Talking about elements and cores, I think yours is, you use external plate heat exchangers. Have I got that right, Ren? Or you have a coil and a plate heat exchanger?
We have, well, it depends. But our current system use external plate heat exchanger coupled with a variable speed circulation pump, so that we can actually determine, plus the additional mechanism. So to be more specific, ATI, aggregate thermal inertia, using this mechanism so that we can determine what the heat rate we want to extract from the heat pump system. Effectively, it's like a virtual buffer, thermal buffer to the heat pump system. And then we can also have a way to reverse the heat from the hot water cylinder back into the heat pump loop. Effectively, that's playing the function of the heating buffer system to either accelerate the heating events or defrost the heat pump.
Mm.
But yeah, we're primarily using a heat pump, but the coil is another option.
Did you have any when you've been doing testing with Valent, have you had any issues around that defrosting? Because that's been a big topic in very recent sort of months about the Valent defrost.
Yeah, defrost is only happening in a very specific condition when the temperature is close to 0 and then it's very humid out there. So you will need a way for that. That's one of the key function of the buffer vessel, is actually to deliver the heat back to the heat pump when doing the defrost mode. And you will definitely need that, because without the buffer vessel, and if it's directly integrated with a radiators, effectively will be sucking heat from your house back to the heat pump during the defrost, and which will then of course cause comfort issues. Hence why we'll definitely need a heating thermal buffer for the system. And when we do that, so that's why we're developing much more comprehensive control, where we're getting signals, like control signals, whether the heat pump is in defrost mode or not. And if it is, then effectively we'll be using the hot water system to provide that heat back to the heat pump system.
Mm. I mean, I know there's some of the Valent engineers I've been speaking to. I think obviously when you purchase or procure a heat pump, or you're looking at your outputs and all this, and it looks like there's been some issues with outputs of kind of maybe missed out some when they've been tested. It's missed out some information around defrost. So that's an ongoing conversation that people are having at the moment among Valent and some of the engineers. It's Damien being one of them. Going back to you, Andreas, the outside units. Tell us a little bit about them then, or is it sort of based? Because I know my listeners, again, they'll be very, very familiar with Kensa, but they're very familiar with this whole thing of district heat networks and ambient loops. This particular device, is this connected to an outside unit?
Well, we have. It was actually part of the project was to develop both an inside and an outside unit, because one of the things we meant to achieve and achieved is space saving. We just talked about the unit is big. It is, but it is still a lot smaller than if you do the same thing with water cylinders, which was the benchmark. And the reason we said we would develop an outside unit was twofold. One, it saves even more inside space. That's the obvious part. And the other one was to get around the issue of using flammable refrigerants, which will be the medium of the future. And if the unit is outside, you're avoiding the issues of needing extra extra ventilation in your installation. So that's why we also developed this as an alternative. Other than that, the internals are exactly the same. Is the idea. It is simply the fact that it's a different refrigerant and can be installed outside, which sort of future-proofs it for us as well, because the F-gas regulations are coming. The question is only when and how, what exactly, but this is going to be the future.
Jonathan, come back to you with because I think the program finishes, doesn't it? What we're in March at the moment. I don't know when this recording will go out, but what's the future looking like for you? Are you going to be working with any other entities to sort of get your innovation out there in the sort of the real world?
Yeah, that's happening at the moment. There's a few demonstration partners that we're working with to get systems out into the real world, but they're just on the two sort of previous points on the demand side response and on defrost that we've been able to do a little bit of work on here. So that the demand side response is really interesting for us, because essentially we're not bound by the same rules that you have to run the compressor for. So we can ramp up and ramp down to zero or at a very low rate instantaneously. You can essentially treat it like an electric heater in that sense, because it doesn't really matter how much you come on for. You can ramp up to meet whatever demand, but you can also sort of preload if you know that there's a sort of cheap time coming up or a tariff rate coming up that's beneficial. And so you can fluctuate the heat pump to do that. It's not part of what we do at the moment, but it's sort of having this project has let us explore that a little bit. So there's definite huge sort of potential there, not even just when you attach it to a grid, but even at the home level, having it tagged with an EV, for example, or with some other kind of thermal store, whatever it might be, whether it's hot water, whether it's a PCM, having some flexibility about keeping it as heat, maybe rather than keeping it as electric. There's still advantages of using a battery, but if you can get the COP multiplier essentially by keeping it as heat, then it's worth doing. But on the other side, on the refrigerant, on the sort of defrost side, there's no sort of reversing of cycles here. There's no way to need to sort of switch over valves or anything like that with ours. It's actually even simpler than reversing it. There's some clever stuff we can do to minimize all that. So there's a huge sort of benefit there that the tech is sort of bringing. And I think for us, it's a case of getting into the market and getting a few sort of pilots out there, and that'll happen over the course of the summer. So yeah, it'd be good to sort of be able to bring that back to you guys and see how they're doing.
Well, it's interesting, your technology, because it's as if it would fit. You could actually sort of take out the gubbins inside a boiler casing and just whack your stuff in, couldn't you?
It's pretty much what we started from. I took a boiler at my flat when we renovated it, and been our like, this is what we want to fit it inside. This is what everyone has space for at the moment. Let's go for this. This is the footprint. This is the package. It's got to be a one-man lift. Let's not make it hard for everyone. It's got to have pipe fittings that you can get into service and look at and check and install. And let's not make this harder than it really needs to be. So there's a lot of stuff that, starting from the ground up, has let us design into with a kind of understanding of where the challenges are. And the goal is still to try and get to 2050. Net zero is the challenge, right? And it's the overarching theme of all this. And I think what we're seeing anyway is this, ironing out where these sort of challenges are and trying to make it simple for people to get up to high numbers of installs done quickly and cheaply and do it correctly. And you still need to, really good heating engineers. You still need the really understanding how the system works, and sort of, you can't change the laws of physics on that, and everything has to be run efficiently, optimally. That still is incredibly important. You've got to stand on the shoulders of giants for this sort of stuff.
Well, it's interesting, this whole thing of space, because you mentioned, and Andreas mentioned space. It's quite interesting because in the UK we've tended to squeeze things into the smallest space possible. So like, we've even done away with cylinders in some instances and just put a combi boiler in a kitchen cupboard. Whereas if you go to some countries, places like Germany, they'll have a basement, like a plant room where all your kit goes on. And just, you're from Austria, I don't know if that's what they do over in Austria, or if they try to squeeze everything into the smaller space. I know the UK has tended to do that, which is kind of causing us all a little bit of a problem now, because people have got rid of their airing cupboards, so there's no space for cylinders now, and the boiler literally is going in people's kitchen cupboards. Is that something that was happening in Austria? Have they still kept sort of basement sort of space for, and the Americans keep basement space for all their plant? What's it like?
Oh, to be honest, I mean, I come from Vienna, so it's mostly flats.
Yes.
A plant room is not on the list. But I do remember from my childhood, actually. I remember that I can only remember always seeing a big cylinder together with usually a gas boiler, of course.
It's part of it, the space thing, isn't it? And obviously it's something you worked with as well, as Ren. I mean, as people have, I mean, you're dealing with cylinders all the time, Ren. I mean, and you've obviously got a cohort of engineers that I should imagine you use quite regularly now, or who use your stuff. Have you seen it as a big problem for people trying to relocate and find space again for a cylinder? Because a lot of homes would have had the space initially, and then they got rid of it and maybe turned it into the ensuite for the bedroom or something.
Yeah, we've seen the increasing more and more people looking into like slimmer cylinders, or so that they can just repurpose their airing cupboard and then put the cylinders elsewhere, such as, for example, in the loft. So they need a slim, like narrow version of the standard cylinder. They can go through the loft hatch and then lift it into the loft. But yeah, we've definitely seen more challenges around it. But again, with a heat pump system, and you are having all the auxiliaries that you need to go somewhere, and I think particularly the whole purpose of that, getting rid of the buffer vessel, is to reduce the whole installation footprint. I think that's where we're aim to help to facilitate and streamline the installation of the heat pump.
Well, gentlemen, it's been fascinating speaking to you, and I wish you all the success in the future. Like I said earlier, we're sort of coming to the end of the program. Unless you're in, are you in wave 2 of Stream 2? Any of you, or are you all in? Yeah, you're all in the first bit. So yeah, thank you ever so much for coming on the show, and wish you all the success in the future. Thank you very much.
Thank you, Nathan.
Thank you.
Thanks for having us.